Chaining is a simple way to handle collisions in a hash table. Imagine a row of mailboxes, the hash table slots. Each mailbox can hold a list of letters instead of just one letter. When two keys hash to the same slot, their records are stored one after another in the list attached to that slot. Structurally, the hash table is an array of buckets. Each bucket points to the head of a linked list or any dynamic container such as a vector. The array index is the hash value h of key modulo m, where m is the number of buckets. The linked list grows as more keys collide, so the overall memory layout looks like. Bucket 0 points to node key A points to node key B points to null. Bucket 1 points to null. Bucket 2 points to node K C points to null. This picture is easy to picture. Each bucket is like a small train station platform where many trains, keys, can wait in a queue. A good hash function spreads keys uniformly across the m buckets. For chaining, we only need the function to be fast, and to compute an integer in 0 to m-1. A common simple function is h of k equals a times k plus b modulo p modulo m, where p is a large prime, r and b are random constants, and k is the key interpreted as an integer. The load factor alpha is defined as n divided by m, where n is the total number of stored keys. In chaining, alpha tells us the average length of each bucket's list. If alpha equals 0.75, on average each list holds 0.75 items, meaning many buckets are empty and few have one element. The expected search cost is proportional to 1 plus alpha, because we examine the bucket constant time plus the average number of nodes we walk through. Keeping alpha low by resizing the table when alpha exceeds a threshold. For example, 1.0 maintains fast operations. To insert a key value pair k, v using chaining, follow these steps. Compute the bucket index I equals h of k mod m. Access the head pointer of bucket I. Create a new node containing k, v. Insert the node at the front of the list push front, or at the end dash front insertion is 01. Increment the total element count ends. The time taken is 01 for the hash computation plus 01 for the list insertion, so the total insertion time is 01 amortized. If we choose to insert at the tail, we may need to traverse the list costing O length of list equals O alpha on average, but front insertion avoids that. Searching for a key k proceeds as compute I equals h of k modulo m. Examine the list at bucket I starting from its head. Walk through the nodes comparing stored keys with k until a match is found or the list ends. If the key is present, the expected number of examined nodes is 1 plus alpha divided by 2, average position in a uniformly random list. If the key is absent, we must scan the whole list, costing expected alpha nodes. Therefore, the expected search time is theta of 1 plus alpha. For a successful search, the constant is slightly lower, but asymptotically, both successful and unsuccessful searches are O of 1 plus alpha. Deletion in a chained hash table mirrors search. Compute I equals h of k modulo m. Walk the list at bucket I while keeping a pointer to the previous node. If a node with key k is found, unlink it. If it is the head, set bucket I to node arrow next. Otherwise, set prev arrow next to node arrow next. Free the node's memory and decrement ends. Edge cases to watch. Deleting from an empty bucket, nothing to do. Deleting the only node in a bucket, bucket becomes null. Multiple identical keys if allowed. Typically delete the first occurrence or all occurrences depending on specification. The cost of deletion is the same as a search big O of 1 plus alpha on average. In the worst case, all n keys hash to the same bucket, making the list length n. Operations then degrade to linear time big O of n. This worst case bound holds for any hash table, because a hash function can map many keys to the same value. The load factor alpha equals n over m does not prevent the worst case, but it influences the probability of it. Keeping alpha less than or equal to 1, by enlarging the table when n is approximately m, ensures that even if a bucket grows, its expected length stays less than or equal to 1, giving average case big O of 1 operations. The formal performance bound for chaining is Expected search, insert, delete time equals theta of 1 plus alpha. When alpha is constant, the bound simplifies to theta of 1. If alpha grows with n, for example alpha equals log n, the operations become theta of log n. The big O of n worst case occurs only when the hash function is pathological or adversarial. Assume we have a hash table with m equals 5 buckets, and we use the simple modulo hash function h of k equals k mod 5. We will insert k's 12, 25, 33, 17, 40. Insert 12, h of 12 equals 2 goes to bucket 2 which becomes 12. Insert 25, h of 25 equals 0 goes to bucket 0 which becomes 25. Insert 33, h of 33 equals 3 goes to bucket 3 which becomes 33. Insert 17, h of 17 equals 2, bucket 2 already has 12 so we chain 17 at the front, bucket 2 points to 17 which points to 12. Insert 40, h of 40 equals 0. Bucket 0 now chains 40 before 25, bucket 0 points to 40 which points to 25. The table looks like, bucket 0 contains 40 then 25, bucket 1 is empty, bucket 2 contains 17 then 12, bucket 3 contains 33, bucket 4 is empty. Search for 12, compute h of 12 equals 2, scan bucket 2, first 17 not a match then 12 found 2 comparisons. Delete 17, locate bucket 2, remove the head node so bucket 2 now starts with 12. If we later insert more keys and the load factor alpha equals n over m exceeds a threshold, say alpha greater than 1, we would resize. Choose a new bucket count m prime, for example double to 10, recompute the hash function h prime of k equals k mod 10 for every key, and redistribute them into the larger table. This keeps alpha around 0.5 and guarantees fast future operations. Explanation: sample exam style questions. 1. Prove that the expected number of elements examined in a successful search in a chained hash table is 1 plus alpha divided by 2, assuming simple uniform hashing. Hint: under uniform hashing, each key is equally likely to appear in any position of its bucket list. 2. Compare chaining with open addressing linear probing in terms of A. Average case search cost, B. Handling of deletions, C. Memory usage when the load factor exceeds 0.7. Provide concise bullet point answers. 3. Given a table with m equals 8 and n equals 12, alpha equals 1.5, calculate the expected cost of an unsuccessful search. Explain why this cost may still be acceptable in practice. 4. Describe a scenario, for example adversarial input, where chaining degrades to O of n time. What strategy can be used to mitigate this risk? Answers should show the derivation of O of 1 plus alpha and discuss practical design choices, such as rehashing and choice of hash function.